Well, here's an interesting example where it's only slightly different than some of the other examples we've had, but we need to remember what this means. And let me just remind us. If I take -1 to the I plus 1, that's either 1 or -1, depending on whether I plus 1 is even or odd. So I know that -1 to the I plus 1 is equal to -1 to the I plus 3. If this is even, then this is even, and they're both equal to 1. If this is odd, then that is odd, and they're both equal to -1. So we need to keep that in mind, and this is equal to -1 to the I plus 5. And I can do the same with -1 to the I plus 2 is equal to -1 to the I minus 2, or I plus 8, or I minus 8. Okay, let's get to the example. The summation I from 1 to n of -1 to the I plus 1 times I is equal to this fraction. -1 to the n plus 1 times 2n plus 1 plus 1 all over 4. We're going to prove that's true for all natural numbers n. So notice what's happening on the left-hand side. That left-hand side is, let's see, when I is a 1, we get -1 squared, which is just 1, so we get 1. When I is a 2, we get -1. When I is a 2, we get -1 to an odd number, so it's -1, so we get a -2. And then we get a +3, and then a -4, and a +5, and a -6, and it goes so on. Okay, well, let's check and make sure that the base case works. And I'll just make a note that that is Pn, what I've got in the box there. Okay, so n equals 1. Let's see if this works. When n equals 1, I is going from 1 to 1, so n is also a 1. So on the left-hand side, we get -1 to the 1 plus 1 times 1. And n is a 1, so we get -1 to the 1 plus 1 times 2 times 1 plus 1 plus 1 all over 4. All right, so what do we get there? Maybe I should have put a question mark there because we're testing it. This is 1 times is 1. Left-hand side is 1. The right-hand side is a 1 times 3, which is 3, plus 1 is 4. It works. The base case works. All right, now we're going to do the induction step, or the induction hypothesis. We'll assume that PK is true to prove that PK plus 1 is true. So we're supposing that this should look exactly what I have in the box above, except that the n's are replaced with k's. So we're assuming that this is true for some arbitrary value of k, arbitrary natural number k. And then what do we need to prove? We need to prove pk plus 1, which would be the summation going from 1 to k plus 1. I goes from k plus 1, 1 to k plus 1, -1 to the I plus 1 times I is equal to, now if k is turning into k plus 1, it's going to become -1 to the k plus 1 plus 1, which is k plus 2, times in parentheses 2k plus 1, where now it's going to go to k plus 1 plus 1. I'm replacing k with k plus 1. That gives us 2k plus 2 plus 3. Sorry. 2k plus 2 plus 1, which it gives you a 3. Plus 1 all over 4. So that's what we have to prove. So this is proposition k plus 1. But that left-hand side, this right here, can be broken down using the inductive hypothesis. It's equal to I equals 1 to k of the same thing plus the k plus first term. So we plug k plus 1 into this expression, make I equals k plus 1, and we get negative 1. K plus 1 gives us k plus 2 times I. And we know what this is here because we're assuming that this is equal to this. So I'm just going to rewrite it with that. Negative 1 to the k plus 1 times 2k plus 1 plus 1 all over 4. And then this term, plus negative 1 to the k plus 2 times I. That, going from here to here, is simply because of the induction step, the inductive hypothesis, where we assume pk is true. This is equal to that. I think I'm going to go to the right here to save some room. And let's see, I think I'm going to do first just a little baby step. Notice, I'm going to get rid of this. That's the same as 1/4. I'm going to break this up into two fractions. So negative 1 to the k plus 1 times 2k plus 1 over 4. And I'm going to put plus 1/4, and I'll do it at the end. Plus negative 1 to the k plus 2 times I plus 1/4. So that plus 1/4 at the end is because I removed the 1 from here. Okay, so now I'm going to factor out. It's going to look weird. I'm going to factor out negative 1 to the k plus 2. And you say, well, there's only a negative 1 to the k plus 1 here. Well, remember, negative 1 to the k plus 1 times negative 1 gives you negative 1 to the k plus 2. So let me write it down. Okay, negative 1 to the k plus 2 is what I'm factoring out. In parentheses, I'm not factoring it out of this, of course, that stands alone. Negative 1 to the k plus 2 times 2k plus 1 over 4. I'm not done yet. Plus, this I is k plus 1, sorry. On that k plus first term, I failed to, I changed this I into k plus 1 plus 1, and then this I needed to become k plus 1. So, I factored that out, so we've got that plus k plus 1 plus 1/4. It's not correct yet. But if I put a negative, I was going to put a negative sign, but instead I'll put a negative 1 times. Now, it looks good. This one's trivial. We factored out the negative 1 to the k plus 2, and it leaves us with the k plus 1 right here. For this one, I factored out a negative 1 to the k plus 2, And it left me with a -1 here. Why is that? Because -1 to the k plus 2 times -1 equals -1 to the k. I could say k plus 3, and I will, but that's equal to -1 to the k plus 1. Because they're the same parity. If this is even, this is even. If this is odd, that is odd. So it does work out. Distributing it through one more time. This term times -1, that's not -1 squared, that's a 2k. That -1 times this gives me -1 to the k plus 1. It gives you -1 to the k plus 3, but that's equal to -1 to the k plus 1. All right, so let me cheat because I'm running out of room. K plus 1 times 4 over 4. That just gave me a common denominator. So now let's see what we get. I'm going to go to the right here. -1 to the k plus 2. And what do we get? This -1 goes with this fraction, so that's really a -2k minus 2. And I'm going to combine them into one fraction since they have the same denominator. I get a plus 4k plus 4 all over 4. Plus 1/4. All right, let's see if I can get it done on this bottom line. -1 to the k plus 2. I want to make it, format it just like this. So, what's this equal to? 4k minus 2k is 2k. And 4... Oh, arithmetic mistake again. -1 times 2k plus 1 is -2k minus 1. Sorry about that. Now it's going to look better. Because this numerator is going to be 2k plus 3. All right. And that is all over 4. And I've got that plus 1/4 that I could combine into one fraction because they have a common denominator, and it would look exactly like this. I'll go ahead and make it. -1 to the k plus 2 times 2k plus 3 plus 1 all over 4. Okay, so it wasn't terrible, but it did require a little bit of work with this -1 raised to an exponent.